Hi, welcome back. So we were talking about equation, and now we will add matrix equation. Okay, we all remember, hopefully we all remember what a matrix is. At least I will do it in the 2 by 2 case, 2 by 2, and the things applies for larger dimension, uh, of course, but it gets trickier and trickier to do the math, and you need to use some heavy notation that at the moment I don't want to. So let's keep it nice and easy. Nice and easy. I already added a few. So there is a little trick here. So you see that these usually I write letters with A and B and C and D, which is fine. But maybe someday I will use a little more abstract notation where we can label these by numbering them with the same letter because the matrix is A and the element will be A, I, J, where I, J are just indices that goes from 1 to 4. Actually, sorry, AI goes from 1 to 4. But then I want to be pedantic and I want to differentiate between rows and columns because if you remember, a matrix is well defined by vectors in rows, columns, and rows. Okay, you can see this vertically or horizontally, and this is the way it's a way to visualize what happens to those vectors in the matrix when you apply it to other vectors. Okay, but just to let you know, then at some point maybe, I don't know, I will use this notation ij, where I goes from, in this case, 1 to 2, and j goes from 1 to 2 as well, because there are two elements for each row or column, and the pairs are 1, 1, 1, 2, 2, 1, 2, 2. It's just a way of counting. First row, first column, first row, second column, first row, and there is a one there. Okay, and then second column, second row. Okay, so yeah, this is just a nice way to order the elements and to refer to the correct elements. At some point, you will realize that elements in different location has also some different mathematical as well as physical meaning. So it's not bad to start playing with the indices in a gentle way, keeping in mind that it can get nasty very quickly, very soon. But don't worry, I'm not going to do that because I can't and I don't want to. Okay, so matrix. So what is a okay? So first off, how does a matrix equation look like? Let's call this matrix A. I will not bother putting some decoration A. Let's just call it A. And let's say A plus, let's say one identity, or let's identity is equal to 0. Okay. Okay. Now, so one way to see this equation, and then the 0 should be thought as a 0 matrix. So the matrix that is 0, 0, 0, 0. Okay. So you need to think about this in an abstract way. So you need to find those elements of A, which when you sum them to the matrix I, you get the matrix. Let's put a hat. Okay, let's do hat because otherwise I get crazy. Okay, hat means matrix in this case. So hat A plus 1 identity, and let's remember what an identity is. Identity matrix is the 1, 1, 1, 1. You see, it's almost like a 1 for vectors, and the 0 matrix is the 0, 0, 0, 0. Okay, good. Okay, now, so in this simple case, we can do exactly what we did with numbers. We just add to this identity matrix. We can bring it the other side if you like. Let's do it more formally. Minus identity. Minus identity. Now, of course, minus identity plus identity cancel out, and we've got a equal to minus 1i. Now, we need to go element by element. So we need to, technically, we need to solve this equation with the, as I will tell you in a sec, but let's do it the easy way. The easy way is just to look at the number a11, a12, a21, a22. This is a, and this should be equal to minus 1, 0, 0, minus 1. Okay. Now you see that this is quite easy to do because you just call this one 0, this one 0, this one minus 1, this one minus 1, and you get your solution. Okay. But okay, this is just to find a matrix. It's not very useful because usually just to play with matrices, because usually, and this is what actually I forgot to do properly. So I mean, this is what I've done is correct, potentially totally useless. But anyway, it's just to get me started. But yeah, I mean, anyway. Okay, so let's do it. Let's do the real deal with matrix equation. So when you have A times X vector is equal to V. Okay, this is an equation. Yes, of course. Before, yes, it was an equation, but not the one that I want to discuss about. Now, we've got a matrix A, and now the matrix A, let's say, is 1, minus 1, 1, minus 1, actually like this. Okay, doesn't matter. There is a reason why I chose this one, and I will tell you why you need to be careful when you choose these matrices. But sometimes you cannot choose a matrix because matrices are given for the physical or the engineering or the math problem that you're facing. So let's start with something easy. And the vector, let's say is, I don't know, let's do 2 and 3. But okay, it's a vector, 2 and 3. And our equation is to find x. X is x1, x2. And you see now that there are two numbers that we need to find, x1 and x2. Okay, so let's do something first. So let's do the multiplication. A times x. This is 1, 1, 1 minus 1, x1, x2. Then you do row by column. So we have x1 plus x2, x1 minus x2. Okay, I can do it step by step. We do this times this plus this times this, and it's the first row. The first row, yes. The second row, let's pick another color, is this times this and this times this, which is exactly this row here. Okay, now this is the first side of the equation. Okay, let's cancel this out and do this remember that is x plus 1 plus x minus 2. Okay, and now this should be equal to, we set 2, 3. Okay, now we need to find, okay, I will do a guessing game at the moment. Let's see if I can find those numbers, and then I will tell you how to do it properly anytime. There are many ways to do that. So technically, okay, let's do, then I will do the guessing game. So first let's do it in a way, which is x plus 1. There are two equations that we need to solve. It's a system of equation, linear equation, okay? One way is to, I don't remember the name of the method, but basically if you sum and subtract, so if you combine the two equations in a way that you can isolate x1 and x2, you can solve the equation easily. In this case, if we sum the first one and the second one, x2 gets cancelled out and you get 2x1 equal to 5, for example. And then if we do the difference between the two equations, we get minus 2x2 is equal to minus 1, because we do the difference. 2 minus 3 is minus 1. And then you can solve them one by one. It's easy now, because we can just divide it by 2, this one, and divide it by minus 2, this one, is 1 over half. And those are the solutions. Let's see if that checks. If we do 5 over a half plus 1 over half, it should be 2, and in fact it's 6 divided by, I did something wrong. If you sum them, we get 5, and if you subtract them, you get plus. You get minus 1, minus 1 half, sorry. Yeah, I was doing it wrong. Minus 1, but you get a plus there, so plus 1. So this is a minus 1. Yeah, so 4 half, which is 2. And then when you do the subtraction of the 2, 5 plus 1 half, you get 3, because it's 6 over 2, which is 3. Okay, so that checks out. This is a way. Sometimes it's not easy to find the linear combination of the equation that you need to find, but you can also guess if you're quick with math. This case is maybe not so easy to guess it. I could have chosen easier number, but now that we know the solution, it's easy to guess. If it were, just saying, for example, 2 and 0, that's easy to guess. If we get 2 and 0, you know that x1 is equal to 1 and x2 is equal to 1 as well, because if you sum them you get 2, and if you subtract them you get 0. Okay, so this was an easy one to guess. Okay, I'm not saying that you should guess, but I'm saying that depends. This is a standard way to do it, but there is a quicker way which gives you also an insight on how matrices deal and works. And I will just briefly mention a couple of things. I won't go into details. I can link to videos that explain that in super nice detail with super nice videos. Not gonna do that. I want just to take on some messages from these videos. Okay, so one way is to use what's called an inverse function. Yes, an inverse matrix, which is very much like an inverse function. Okay, let's call it e to the minus 1. That's an inverse function. First, the definition of an inverse matrix is that when you apply to a matrix, you get I. Okay, the same way when you, meaning that if you put an x, you get an x. The same way that the inverse function of x, f minus of x is equal to x. For example, logarithm and exponential, square root and square, I don't know, arcsine and sinus, etc., etc. So, oops. So the inverse function is something that we didn't touch much about. I used them. I told you that sometimes you can flip the graph to see if you can. Sometimes there are multiple values that you can't, so you have to restrict your values. Anyway, inverse function, whatever it brings you to the initial point. Matrices are kind of the similar way. You find a matrix that multiplied by your matrix get the same value of x, so the identity. Now, not every matrix can be inverted, okay? And this is due to the fact that in some way that I'm not going to discuss, let's say these are points, let's call them vector. This matrix, it's invertible if all the vectors go to different vectors, the same way that we did it for a function. You can do it with vectors. If some of these vectors, not all of them, but it's enough that some of the vectors get mapped into the same vectors, okay, this is already enough to say that the matrix doesn't admit an inverse. Because for those vectors here, you cannot go back and uniquely identify your initial point. So you cannot solve the equation basically because you have multiple solutions and you're not happy with it. Or maybe you are, but maybe that's what you, I mean, I'm saying that that's not a way to, let's say that's not the solution of the equation. There are multiple solutions. Okay, so matrix invert is very similar to inverse of a function. But what's the definition of an inverse of a matrix? So the definition is 1 over the determinant, and I will tell you what it is, of a matrix times the adjoint of a matrix. Okay. I know it sounds confusing, but it's not, because the adjoint of a matrix, let's say transpose. Not sure about adjoint. Just checked in Wikipedia. But maybe they have a different definition. Let's use transpose that I think it's correct. Transpose. With this is trace. So let's, sorry, I'm messing up with the notation. Let's do it the way that I remember it's correct. And then we can discuss about it. Transpose, ATA. So AT, A to T is transpose. And means that you swap the row and the column. So A11 stays there, A12 goes there, A21 goes there, and A22 goes there. As you can see, with respect to A, the difference is in the off-diagonal terms that get swapped. Okay? So this is the transpose. Basically, you rotate the column in vector, in row, and the row in column. And this is the transpose. While the determinant is a very important tool in mathematics and in physics as well. It has some geometrical and physical meaning. I'm not going to discuss it about now. I'm just giving you the determinant of a 2 by 2 matrix So it is, which is a number, and it's A11 times A22 minus A12 times A21. Okay, in this case, it's this number here. So you go diagonal, you multiply the diagonal, and then you multiply the off diagonal, and you get a minus there. For higher dimension, it's more complicated than that, but for the 2 by 2 case, it's as simple as that. And you put it down there. Now, we can already see why it's not always true that this matrix here exists. Because look, the determinant is on the bottom of a fraction. The transpose always exists because it's just flipping the row and columns, nothing major about that. But here there is a difference. So what about when it's 0? If a difference of two numbers is 0, you get 0 in the denominator. And 1 over 0 is infinity. So it's not a good number. So bear in mind that the determinant of a matrix needs to be different from 0 if you want to have an inverse of a matrix. Okay, so the determinant different from 0 if you want to have an inverse of a matrix. Now, this is good because our matrix has in this case, has a determinant which is different from 0 because 1 times minus 1 minus 1 times 1, which is minus 1 minus 1 minus 2, which is different from 0. And in fact, our inverse matrix would be, let's write it down here. We know what a determinant is, at least in the 2 by 2 case. Not giving you much more details on that. So first of all, the transpose is 1 minus 1, 1, no, 1, 1, 1 minus 1 is the same. The transpose is the same in this case because we swapped the diagonal term there. Different, but the determinant is 1 over minus 2, so we get minus 1 over 2, minus 1 over 2, minus 1 over 2, minus 1 over 2. And if I didn't do any mistake, this matrix should give identity when I multiply by the initial matrix. Let's hope it works. And then we can use that to solve the equations. So how do 1 minus 1? This is our initial matrix. And then we multiply by minus 1 over 2, minus 1 over 2, plus 1 over 2, which is minus actually, and then plus 1 over 2. Because this is minus, 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 and plus. Sorry. Let's see if it works. So the first one is, and I think I got it wrong, plus, this is minus 1 times minus 1, because it's the absolute value. Sorry, there is an absolute value in the definition is absolute value of the determinant, and then a minus 1, a minus 1, which means that this is 1, 1, 1, and minus 1. And this is, the determinant is then 2, because there is an absolute value, meaning that you remove the sign of mine. This is plus, 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 minus 1. And this is 1, and this is 0, and this is 0, and this is 1. So you get identity. So sorry about that, I forgot the absolute value. So we need to get the absolute value there. Remember, the absolute value of x, of mine of x, is x, and the absolute value of x is x. So basically, whatever sign you get, you always get a plus when you use the absolute value. Okay, and okay, so this formula here works. I think the Wikipedia ones use a different. I need to check that. Anyway, I will link it and then we can discuss if needed. But anyway, so this is the one that I want to use. So, and then I will stop, and then I will finish off with the differential one. I thought it was quicker to get to those ones, but I wanted to give you an idea of the equation, because all of these then can be used together. You can have differential matrix equations, for example, which I may not be going to. Well, maybe yes. So let's go step by step. Anyway, let's do one thing first. How do you solve this equation formally? Ax equal to v. Now, if there is so if modulus of the determinant of A is different from 0, you can multiply by minus I minus A inverse both sides, because you know you have to do the same thing on both sides to get the same answer in the end. This is identity. X is equal to A minus V. Now this is something that we can compute because we know V, we know A minus 1, and we get X. Okay? And then we can check that our result is correct. So remember, the determinant needs to be different from 0. You use the transpose, you get the inverse, you apply the inverse, and you solve for the X equation. Okay, next video is about differential equation then, and then I will stop for today and give a brief summary of what we said. See you later.